The learning objectives for this training module are combustion fundamentals, fire and explosive requirements, explosive limits, auto ignition and flashpoints, explosive groups, IEC classifications, temperature classifications, methods of protection, and electrical device markings. A combustible gas or dust explosion may exist in a variety of industries, including petrochemical and refining, food processing, pharmaceuticals, and fossil fuel power generation. The vast majority of organic and synthetic materials, as well as some metals, can form combustible dust. Combustion or fire is a chemical reaction in which a combustible material combines with an oxidant to release energy. Part of the energy release is used to sustain the explosion by utilizing existing heat or creating a vacuum to consume more oxygen. Within a hazardous environment, there are three elements necessary for a fire or explosion: a combustible material, also known as a fuel, ignition source, either electrical arcing or general heat, and an oxidizer, also known as oxygen. When a fuel, oxidizer, and ignition source are present at the necessary levels, burning or explosion will occur. To reduce the possibility of fire or explosion, one of the key elements needs to be reduced or removed. Another key factor in a fire or explosion are the explosive limits. These are the maximum and minimum concentration needed of a given combustible material to support a fire or explosion. To form an explosive mixture, the hazardous gas must have sufficient concentration levels. The minimum concentration of oxygen to combustible material is known as the lower explosive limit, or LEL. If the concentration is below the LEL, it will not be flammable or have enough flammable material present. The same condition would apply if gas concentration is too rich, meaning it will not ignite because it will not have sufficient oxygen to sustain the fire or explosion. This is known as the upper explosive limit, or UEL. It should be noted that different gases will have different threshold limits. In this example, the LEL of hydrogen is 4%, and the UEL is 75.6%. Therefore, any mixture of hydrogen and air that falls between these limits will have a flammable mixture. In addition to the explosive limits, each hazardous material will have an auto-ignition temperature and a flash point. The flash point is the temperature at which the material will generate sufficient quantity of vapor to form an ignitable mixture. As the liquid is heated and reaches the flash point, auto-ignition could occur. An auto-ignition is the lowest temperature at which a combustible material will spontaneously ignite in a normal atmosphere. In this example, we have the heating of a combustible liquid. Explosive vapors are created as the material reaches the explosive limits, creating the flash point. If the general atmosphere is increased to the auto-ignition temperature, fire or explosion will occur. To simplify the specification of electrical devices into hazardous environments, IEC classification methods utilize auto-ignition, flash point, and explosive limits to place the hazardous materials within groups. The two predominant methods used for classification of hazardous environments are the NEC and IEC standards. IEC and NEC standards both classify the level of risk into three main categories: continuous, occasional, and not normally present. All three categories provide the likelihood of an explosive atmospheric condition within the general environments. Within the IEC standard, the general risk categories are then classified as zones. This reflects the physical material that could provide a potential fire or explosion. For liquids and gases, the area classifications are Zone 0, Zone 1, and Zone 2. By altering the physical material to dust or fibers, the area classification numerical value changes to Zone 20, Zone 21, and Zone 22. Referring back to the necessary requirements for an explosive triangle, we know we need an ignition source, oxygen, gas, and/or dust combustible material in the correct mixture within the atmosphere. In order to specify electrical devices and hazardous locations, we need to identify the general zones within each area. When working with liquids or gas, we locate the most hazardous or flammable location directly above the material. Due to the possibility of the valve leaking at the top of the containment structure, we must classify the area as Zone 1. As we move further away from the possible explosive atmospheric condition, the zone classification would be reduced to Zone 2. By altering the combustible material properties to a solid form, the area classification above the material would be Zone 20. If the dust escapes the same failed valve, the external area around the containment unit would be classified as Zone 21. As we continue to move away from the containment unit and with reduction of category risk, the new classification for the general area would be Zone 22. Now that we know combustible materials, whether liquid, gas, and/or dust, will have different upper and lower explosive limits, and we understand that general heat could be the ignition source, within the IEC standards, the T rating specifies the maximum surface temperature an electrical device will create. As the temperature increases, the associated rating will decrease, meaning less heat will have a higher T rating, while an increase in surface temperature will reduce the T number. As a recap, the IEC standards classify hazardous areas as environments that could contain explosive vapors, gases, and/or dust within the atmosphere. The primary categories provide the risk levels as constant, occasional, and not likely. Since elements have a variety of flammability and the physical properties could be different, IEC standards segment the types of combustible materials into zone classifications. The most hazardous is Zone 0 or Zone 20. By reducing the risk level to have occasional explosive atmospheres, the zone classification is Zone 1 or Zone 21, and further reduction of category risks would change the hazardous classification to Zone 2 or Zone 22. Let's take a look at each method of protection and the general application. To ensure safety in a given situation, equipment is placed in protective level categories. As mentioned before, Category 1 is the highest safety level, making Category 3 the lowest risk and safety level. The general 8 protective methods are flame-proof enclosures, sand encapsulation, pressurization, oil encapsulation, general encapsulation, increased safety, intrinsic safety, and non-sparking. The flame-proof method is a type of protection where devices that are capable of igniting an explosive atmosphere are built inside an enclosure. This protective method prevents the transmission of the explosion to the external atmosphere surrounding the enclosure. This method of protection would be suitable for applications on power-operated equipment, switchgear, motors, and any equipment that produces an ignition source during normal operation. Sand encapsulation is a type of protection in which the enclosure of the electrical apparatus is filled with a finely granulated material. This ensures electrical arcs occurring within the electrical apparatus will not ignite the surrounding atmosphere. Pressurization is a method of protection by which the entry of a surrounding combustible material is prevented by maintaining a protective gas within the enclosure. This is generally accomplished by creating a higher pressure within the enclosure than the surrounding atmosphere. This protective method would be used for any power-operated equipment. Oil encapsulation is a type of protection in which the electrical apparatus or part of the electrical apparatus are immersed within an oil-based fluid. The general application for this type of protection would be used for switchgear units, circuit breakers, and transformers. Encapsulation is a type of protection in which the device that could ignite an explosive atmosphere are enclosed within a resin. The material used would be resistant to environmental influences, heat, and/or sparking from electrical components. The general application for this protective method would be used for electrical circuit boards, miniature motors, and valves. Increased safety is a type of protection where measures are taken to prevent the possibility of high temperatures and the occurrence of ignition. This method includes the interior and external portions of the electrical apparatus. The general application for this protective method would include connection and distribution boxes, luminaires, measuring instruments, and devices that do not normally produce ignition within operation. Intrinsic safety is a protective method to ensure that the available electrical and thermal energy in the system is always low enough that the ignition of the hazardous atmosphere cannot occur. This is achieved by ensuring that only low voltages and currents enter the hazardous area, as well as All electrical supply and signal wires are protected by safety barriers. The general application for intrinsic safety would be used for measuring and control engineering, data engineering, and low electrical valves. Non-sparking equipment and wiring process is a protective method where apparatuses are designed with low power levels and low stored energy. This ensures that an arc produced during normal functionality of the equipment or as the result of equipment failure has insufficient energy to ignite the hazardous atmosphere. The general application for non-sparking protective methods would be used for motors, lighting, junction boxes, and electrical equipment. All equipment certified for use in hazardous areas must be labeled to show the type and level of protection applied. In this example, we will review a fluorescent light fixture within a hazardous environment. The first identifying mark will reflect the apparatus group by hazardous application. A 1 would indicate usage for coal mines, while a 2 would indicate general industrial environments. The next identifying mark is the category risk level. As mentioned earlier, there are 3 category risk levels that would identify the occurrence of an explosive combustible material. The next mark identifies the type of combustible material within this hazardous environment. The available option would be the letter G for gases or the letter D for dusts. The next mark identifies this fixture as manufactured to meet the European standards. The next letter indicates the type of protective method used. Referring back, the letter D would suggest the electrical device utilizes a flame-proof enclosure. The next number and letters will identify the explosive gas group. Remember, the gas group provides the critical information on the combustible material's explosive properties. The final marking provides the maximum surface temperature of the fixture during operation. In summary, hazardous locations could exist in multiple industries. The geographical location will dictate the general method used for classification. The European Standard, or IEC, provides guidance of risk into 3 main categories. These risk levels are then divided into zones and have numerical values that relate to the possibility of explosive gases or dust present within the atmosphere. Because combustible material could have a variety of explosive limits, the method of protection will be important. Nevertheless, all electrical devices placed within hazardous environments will follow the device markings to ensure fire or explosion does not occur.